Namaskar, Dr. Garg.
नमस्कार जी
Good evening. How are you?
कैसे हैं?
मैं तो बिंदास हूँ, feeling lighter than ever.
Yeah, that's good. So you're having all this. I can see, your puja room. It seems.
Right.
That's
With the
good.
Ayodhya Dham on the top.
Well, that's good.
This is also from Ayodhya.
Yes. Have you been to Ayodhya?
Yes.
Okay. So you went recently after the inauguration?
I went for the Prana Pratishtha itself.
Oh,
I was lucky.
that's good. So, well, when we go to India sometime, we would definitely go to visit Ayodhya. But I think it's the biggest gift to India.
Absolutely.
India, which this government or whosoever is given, whatever.
Right.
Although
the government had its role to play, definitely.
Yeah,
But there's so
goes
many,
to, of course, Yogi ji or
generations
Modi ji.
of people who have been involved from various
a lot of
fields,
people have
including
sacrificed.
the judiciary, and of course, yes.
So, okay, so let's. How many have joined?
And Dr. Keshav Kumar is here and Shiva Gautami.
Okay.
Namaskar, sir.
Namaskara, Keshav.
Good
how are you?
evening.
Good evening.
Namaskar, everybody. In India, have they started now more of a Jai Shri Ram?
Yes, more confidently.
Yes,
I think it was always within the heart, doing it silently, but now I think it's bursting out. It's high time it did half a millennium later.
I think our Indian way of this Namaskaram, it's the best.
Absolutely, absolutely. From so many different aspects. One is from the spirituality, but also even from hygiene, especially during the COVID pandemic. I think a lot of people realized that. And many Westerners also started doing namaskar instead of shaking hands or hugging. Because there's something called the runanubandha. When we have a physical contact, there is something called the runanubandha, where we transfer a lot of our vasanas and samskaras. So this is the best way to be light and essentially transmit only the spiritual energies rather than anything else.
I also I love always whenever here also when I meet anybody, any Indian, we always say namaste. I don't like to say good morning, good afternoon, hello. That's
right. Yeah, some at least good morning and good evening have some meaning, but hello and hi have hardly any meaning.
That's right.
It's nice to have Dr. Manju also, even after his retirement from NAL, he's still continuing to participate.
Hello, Professor.
Hello.
Nice to
Hello,
good evening.
Professor Garg.
Oh, good afternoon. How are
good
you?
Afternoon to both of you.
Oh, it still is a bit thin. Let's wait for a few more minutes and then we can start. And so I think what I wrote to you that I would cover the certification, and I hope it might take about 3 lectures. And if it takes more, I don't mind continuing.
Rushed. So please don't feel rushed. So
yeah, I can
whatever
continue.
works best in terms of the learning and the knowledge transmission, I think that's what is more important.
All of these notes which I had given, quite a few slides, in fact, almost 25 to 30% is repetitive information, which I've already delivered in various lectures, but I don't want to cut off from my certification because it's a full time. Everything is there. That's why I wanted to retain all the information which I already covered, even though those otherwise, there's a continuity loss. So, okay, I think there are 5
people, we can get started,
attendees, and I could start now.
Yeah,
okay.
Please go ahead. Thanks for everybody being here.
Good afternoon. Namaste, everybody. And so what I'll be doing now, let me just share the screen. And I'm just opening my first the slide from the introduction. That is the first lecture. That what we intended to do in the course was I covered various topics as you see here. Only the red line, red lettered topic I have not covered. So I covered introduction, micromechanics, macromechanics, free hydrostasis, delamination behavior, laminate design guidance, and stability. As I said, I haven't covered, even though I was thinking I had prepared the notes. But later on, if there is interest, I might, depending upon my condition also. Notches and holes are covered. Bolted joints, adhesive bonded joint, history of aircraft failures and design criteria, damage tolerance diagram, damage tolerance analysis and design of structures, fatigue of composite structures, and testing and evaluation as a separate topic I haven't covered, but quite a bit of a testing and evaluation part I have included in the certification document. So I thought probably it might be unnecessarily redundant if I cover testing and evaluation separately, because those notes also contain large amount of commonality between certification and testing and evaluation. So these were the topics which I had intended to do. And out of this, basically, I believe, except the stability criteria, which I have not covered separately, but let us see, I can provide my lecture notes on stability if I don't cover it. But anyway, it depends upon the interest, however. So let me just go to the today's topic. We'll be starting as a certification philosophy of composite structures. Now, most of the presentation in this is based on the 787 program with which I was associated within Boeing. So many of the slides which have been presented in this are from 787 program, which is in a public document, public domain. So basically using that my public domain material, which is mainly from a certification lecture in a conference several years back I presented. So let's just show this in introduction. So this presentation includes certification philosophy for commercial aircraft composite structures with an emphasis on Boeing 787 movable trailing edges. So all the examples which I have correspond to this 787 trailing edges. And this example is based on the paper, as I said, which I had presented in 2013 in SAMPE. And that is why I could include that material in my presentation, as it's in public domain. I've listed various references in this presentation. It may not be all the references which I might have used in this one, but majority of references which I've used for presentations are included in this. And so some regulations references. Okay, now contents for this lecture is certification definition, unique features of composite structures, approach to certification, usage of composites in aircraft, Boeing 787 MT components, that is movable trailing edge components. Structures fatigue and damage tolerance diagram, damage definitions and sizes, durability, structural analysis, fabrication process, introduction to building block approach. Now, what you see, these six blocks, which correspond to basically the testing. There are few details are included in this presentation. Of course, I can't include everything for testing details, but if there are specific questions regarding particular tests, I am willing to elaborate. And then conclusions. So this is a summary of the material to be covered in this presentation. Now, significant amount of material which is included in this presentation might be repetitive, which I have covered earlier in my lectures. So please bear with me. If you find the repetition, I would not be elaborating on that repetitive slides, but I would briefly touch them. It is just to refresh the knowledge and also to maintain a continuity of this lecture. Okay, now what is a certification? We talk of certification. Certification has to be done for any product which you design, whether it's a furniture, according to certain standards, automobile, aircraft, anything, medicines, everything has to be certified by certain regulatory agencies if you want to sell the product. Same thing happens with aircraft. So certification of an aircraft is a confirmation to its approved design. That is, design which you have designed or company has designed is approved according to the specifications which were provided by the manufacturer. Confirmation of manufacturing processes and is a condition of safe operation. When you are selling the aircraft, designing and selling, manufacturing, selling the aircraft, you have to get the certification regarding the design, manufacturing processes, and the operation. And we'll see in the following slides the details of this. That means certification ensures the safety of the product. So basic objective of a regulatory agency is to ensure the safety of the product so that it does not affect the safety of the passengers and other property. So certification has three major elements over here. One is the design, another is the production, and third one is the airworthiness. So approvals for all these three have to be given before the manufacturer can deliver the aircraft to the customer. So what does design approval means? Design is approved, and when the design is approved, the regulatory issues a type certificate. Now, what type certificate means? The approval is given for a particular type of aircraft. And that is, the company has to adhere to all the specifications designed for that type. You cannot make even a minor modification without getting another approval from certification agency. And we'll discuss the details of this in next slide. Production approval. Production is in accordance with the approved design and quality system. And then regulatory issues a production certificate, product manufacturing approval. So when production certificate is issued, then the regulator or their representatives will visit the factory, the manufacturing organization, they would look into all the facility, approve the facility, and that all those facilities have to be maintained according to the regulatory agency. Then there is an airworthiness approval. That means airworthiness approval is given, conforms to approved design and safe to operate. Okay, what is this type certificate? Let me just elaborate on this. It's an important terminology. Now, TC is issued by the regulatory agency to reflect that the type design is in compliance with the airworthiness requirement. As I said, the particular type design, the specifications for which you have designed, and all the details of the design, they are in compliance wherever it's required. The airworthiness of the approved design type or type of an aircraft to be manufactured. You cannot change, as I said, that you cannot change any specifications, any design detail, any manufacturing process once it has been approved. TC once issued, the design cannot be changed unless at least part of the process for certification is repeated to cover. So suppose Boeing 787, a model was produced, say -8 or -9 or -10. Each one, of course, was certified when the changes occurred. But suppose there's a particular model and you think it was designed with a particular type of a hinge material, a fitting material. And you think earlier it was a titanium fitting. Titanium is expensive. And then further research, design changes may say that you can use aluminum. So if you want to change the titanium to aluminum fitting, again, that means you have to get an approval from regulations. If there are major changes, again, you might have to test a part of the component in order to show the validity. So that's what it says. Once the type certificate is issued, you cannot make any changes. And if you make any changes, you have to get again approval from the regulatory agencies, depending upon the amount of data you submit for design, testing, and then they have to be satisfied with the change. Okay, type certificate including amended and supplemental type certificate. So what happens supplemental type certificate is when some changes are there and then the regulatory agency may issue a supplemental type certificate or approved design under product manufacturing approval, that is a design approval, that is given as a technical standard authorization, letter of TSO design approval or other approval. So these are documents which are given in order to approve the design by regulatory agency. And production approval. So a document issued by FAA that allows the production of a product or article in accordance with the approved design and approved quality system and can take the form of a production certificate, a product manufacturing approval, so a production certificate, or a technical standard order obligation. Airworthiness approval, a document issued by the FAA for an aircraft engine, propeller, or article, which certifies that the product conforms to its approved design and is in a condition of safe operation, unless otherwise specified. So once the airworthiness approval is issued, then of course, then customer or airline is able to operate that. So these are three major elements for the certification. Type inspection authorization. This is another terminology which you will see in my next diagram, the type TIA. Now what happens, TIA is issued which authorizes the official conformity, airworthiness inspections, and flight test necessary. So once the design has been approved, Then what happens? The regulator issues a type inspection authorization to the manufacturer, which authorizes that they can start doing flight testing. You cannot do the flight testing until you receive a type inspection authorization. Okay. Then what does it mean? Fulfill certain requirements, type certificate, supplemental type certificate, amended TC and amended STC. This is the objective for issuing TIA. Now, here, this is a flow diagram which I have taken from the Composites book, MC New, and a few changes I have made appropriately in this. So what you see, this is a complete certification process for the aircraft. Manufacturer, application for type certificate, airplane specification report, and certification plan. This is what you have to submit your specifications, certification plan as an application for type certificate to the regulator. And after receiving that, studying that information, the regulator assigns the project number. And then manufacturer starts designing the product, drawings, loads reports, structural analysis report, all that material and process reports, testing report, all that material then, after they have designed, tested, validated everything, then they submit the material to the regulator. Regulator reviews the design, and then manufacturer also conduct the structural and materials test. In fact, this is included here also. This, because manufacturer conduct a structural material test, it is not that after this one, simultaneously along with this one, the material test also occurs. And then all this document goes to the regulator for type inspection authorization. This is what I said in the previous slide, that after reviewing the design, then the regulator authorizes, okay, you can proceed further for flight testing, and manufacturer then performs the flight testing, and then final TIA test report, all the TIA test report, final design package is submitted to the regulator to get the type certificate. This is what the flow chart contains as just a general flow diagram for the certification or getting a TC from the regulator. Of course, all this process would take billions of dollars for a new project and millions of working hours. Similarly, for the military aircraft certification, I do not have any flow diagram because that may very much depend upon the type of the aircraft, military agency, and the process between the manufacturer and regulator would be negotiated for the process. So this standard flow diagram cannot be given. So a flow chart for military aircraft will be different to civil aviation and is not provided here. Okay, certification. What are the main elements over here? One is manufacturer, naturally. There are two stakeholders, manufacturer and regulator. That means next is a design analysis, testing and evaluation, manufacturing. These are the major elements over here. And then you have a documentation, which is submitted to regulator, and product certification. Just very briefly, I have prepared this flow diagram for this. Are there any questions so far? Hello? Any questions from audience? No? No. What happened?
You can either unmute and ask, or you can post your questions on Q&A. I don't see any questions in Q&A right now.
Yeah, okay. I thought, just asking orally the question, I would welcome, but seems no question. Let me continue. Now, certification of composite structures. Earlier aircraft, in 60s, 70s, mainly were metallic aircraft, and all the regulations at that time were written for metals. Of course, when the composites came into picture, some of the requirements changed, and I'll talk about that later on. So regulatory requirements, certification of composite structures. According to the regulatory agency, as far as the requirements for the composite structure is concerned, it is the same reliability and safety required for composites as for metallic structures. So there's no difference in the requirement whether it's a metallic or composite, because the regulator is looking for the safety and reliability. So they need to ensure the same amount of reliability and safety, whether it's a metallic or composite. However, composites being unique in terms of the materials and process require additional considerations for design features compared to metallic materials. Because there are many issues with the composite materials which are different to the metallic materials. And some of those differences I had covered during my introduction lecture, but I have included a few slides from my introduction lecture also, just to illustrate again certain key factors for the composite materials. So unique features of composite structures. One of the basic things for the composite structures is it's not isotropic material. Metals, they are macroscopically isotropic materials. Composites are heterogeneous nature materials, which are anisotropic, because anisotropic means they have directional property, whereas metals, we always treat them isotropic, that is in each direction the properties are same. Although even for metal, that way, like a longitudinal direction, transfer direction, and LT, slightly, because of the grain differences, there's difference in the properties like a strength, slightly, but not much. We don't differentiate only at the time of, when we are doing the margin analysis, we would consider the minimum strength in a particular direction, and you are designing like a lug and many of the structures where you have to really care for whether you want to have that particular direction as L or LT or T, all those things. So, but we don't treat that as an isotropic material because the stiffness is same in all directions. In composite, that is not so. Through thickness, stiffness, and strength is very low. Then another thing is environmental sensitivity. Strength, stiffness, they degrade. Of course, stiffness does not degrade significantly compared to the strength with the moisture and temperature. It doesn't happen with metals. Metals degrade only at a very high temperatures, but at normal temperature of operations, there is no significant change in their properties. Another thing, complex failure modes, which I have talked several times during my lectures on damage tolerance and damage type behavior, about the failure modes and the failure criteria for the composites and aluminum, and the represented picture, which I have again shown earlier in my other notes, that aluminum, when you are loading it, then it can have a self-similar crack growth, the crack proceeding in the same direction as the initial crack or normal to the load direction, principal load direction. Here, you find a multiple type of damage levels in composites. So there is no self-similar crack growth. The damage propagation and prediction, fatigue and damage tolerance, which is different, as I have discussed earlier during my earlier notes, earlier lectures, that say when aluminum self-similar crack growth here, significant or damage, there is no single crack. Complexity of analysis, because of anisotropy nature of the materials, and also, as you see, the damage behavior is quite different compared to metals. The analysis becomes much more complex than metallic materials. Other features are material reliables and lack of data. A large number of tests required in order to generate the reliables and design information to validate the composite materials. Whereas for the metals, certain, like aluminum, when you're using, there's tons of data available in terms of the handbooks, like Mill Handbook 5, containing the material data for various aluminum types, steel types, titanium. So there's standard data available. Whereas composites, it's very hard to find standard data because no company would ever publish in a public domain. They keep it proprietary data. Then processing of composite materials is quite different to metallic materials, and there are many types of different processes which one will use. Materials and fabrication process variations, lightning strike damage protection. This is another issue with the composites, because composites are inherently low conductive materials, and it creates some kind of more damages compared to metals when lightning strike occurs. So lightning strike protection has to occur. But strike damage, because type of the damage, which on a metallic aircraft would be different to composites. So that is another area which you need to consider. Galvanic corrosion. I talked earlier about what happens with aluminum, and there's some electrolyte, mainly the water, moisture between aluminum and carbon, and the electronic current flows, which causes the leaching of the aluminum, that is corrosion of aluminum. So in order to basically protect the aluminum from corrosion, when you have aluminum sitting over a carbon skin, naturally it's likely to corrode. So what happens, in order to prevent that corrosion, some kind of a barrier ply is introduced between carbon and aluminum. So a glass fiber ply normally acts as a barrier. Then fire safety, there are certain fire safety issues maybe there for the composite materials compared to aluminum, and structural repairability, that's another concern. So these are some of the factors which need to be considered while considering the difference between the aluminum component and composite components. So surely, from analysis point of view, the analysis of composite becomes more expensive compared to aluminum. But nevertheless, in spite of having all these differences and complications of the composite structures and the various issues, at the end of the day, composite structures are still seem to be more efficient than aluminum. And that is why there has been a significant increase in the usage of composites in the aircraft industry. Major regulations relevant to structural design and validation. I've shown this slide during my introduction that major regulations for structures are 14 Code of Federal Regulation, Part 25, which is for larger transport, certain regulations like loads, factor of safety, strength and deformations, proof of structures, crashworthiness, material strength properties and design values, lightning protection of structures, aeroelastic stability, materials control, process control, continued airworthiness, repairability. So some of these items or regulations I've listed over here. Nevertheless, there are hundreds of regulations which you have to meet. And then another is associated with this one for composites, because what happens, these regulations are general regulations which mainly cover, metal. It doesn't say it's only for metal, but the requirements are written in terms of metals, basically. So what happened when the composites were introduced, and due to certain differences between the behavior of composite and metals, then FAA developed a modification, another document, an amendment, which is advisory circular, which is called Advisory Circular 20.107. First edition was A. This B is another issue, which I think was published sometime in 2010 or 11, I don't remember. So what it does, AC 20.107B sets forth an acceptable means, but not the only means of showing compliance with the provisions of 14 CFR Part 23. Part 23 is for small airplanes, Part 25 for large airplanes, 27 and 29. Regarding airworthiness type certification requirements for composite aircraft structures involving fiber reinforced materials, that is carbon and glass fiber reinforced. So what it is doing, this document or advisory circular is a means of compliance of the regulations for the composite structure. That is, what happens in order, how do you meet those requirements, like say damage tolerance requirement. The document, which is FAR 25.571, mainly is for metals. And there are certain differences, as we have discussed, for the composites damage tolerance. And that is why this document AC 20.107B provides the guidance. How do you meet those requirements for the composite structures? So it contains certain sections which I have listed over here. And all these documents, FAA documents, you can download from FAA, free of cost. So materials and fabrication development, prove a structure is static, prove a structure fatigue and damage tolerance for composite. How do you meet those requirements? Proof of structure flutter and other elasticity. Continuity airworthiness. Additional considerations like crashworthiness, fire protection, flammability and thermal issues, and lightning protection. Design certification approaches. Any questions so far? It has been very quiet. I would like to hear from the team. Anyone? Volunteer? Is it interesting? Is it useful material for you? Some of you from NL?
Yes, Professor.
Yes, please go ahead. I just want to know,
Yeah,
carry on.
Yeah, it looks fine, Professor, but still we have to learn actually. Okay, so after your lecture, maybe we have to again go through that again. We can have some doubts. Then we can post you through either email or next classes.
Sure.
Okay, so it is quite interesting. Yeah, it is very useful for our kind of organization, NL.
Okay, that's good.
Professor,
yes.
This environmental sensitivity and flammability, how do we demonstrate to the certification authorities?
Environmental sensitivity?
Through test, that is, should we take a higher factor above 1.5 and demonstrate?
No, actually, in fact, what happened during, I think my macromechanics and other analysts have already made it clear that you had to assess your material strength, stiffness behavior by allowable testing.
Yes.
Okay. So when you are testing, suppose compression is critical. Not every property has to be tested. So suppose you are testing the coupon for open hole compression. So you have tested some coupons at room temperature, some coupons at hot wet condition, like 160 F or 70 degree F, 70 degree C, after soaking into the moisture, and at the cold conditions, so various temperatures, moisture contents, you will be testing. Of course, normally you will do around 3 or 4 at the lowest temperature, room temperature, and the highest temperature, and draw the graph.
Yes.
Okay. So what happens there? You have to consider, suppose our transport aircraft operational, normally we consider around 70 degrees centigrade operational limit, higher temperature. Yes. So you have soaked the coupon for almost saturation for 2 months or 3 months, as long as it takes for saturation criteria. I can talk during my testing and reliables. How do you do that? So once it has absorbed the moisture or equilibrium moisture content, then you are testing that at higher temperature, like 70 degrees centigrade. And then that coupon might show almost 20% degradation compared to your room temperature property.
Yes.
Okay. So that means when you are determining your strength margins, you are using the lower reliable, not the room temperature reliable.
Yes.
And that is what takes into account your environmental factor.
Yes.
And when we are testing the full component, we don't test at a higher temperature and moisture.
Yes.
It's no use putting the aircraft into a chamber and then testing it. We can't do that. It's impractical. So what you do, all these environmental studies are done by the coupons. Determine your knockdown factors. Testing is done only to verify the analysis method.
Okay, Professor. Actually, coupon level, we take the reduced strength and we do the analysis. But a flight component to qualify, what I asked was whether we have to do a test for a higher load, say 2 times the limit load, like that.
I'll talk about it, but you don't test. You actually, according to our testing philosophy, we determine the allowables, all design values, all the factors, whatever the factors are there, design, different knockdown factors would be there, like notch effect, hole size effect, radius effect, all those effects are considered, material effect, design. Finally, you will determine the statistically based allowable. Because you have considered all those eventualities.
Yes.
And so you have already knocked down the allowable. Okay. Once you have designed it, your load is particular. You are designing for ultimate load carrying capability. So you have designed the air structure for ultimate load carrying capability. Approach is just for the zero margin. You don't want to carry unnecessarily weight by having a margin. Okay, I want to have some safety factor. Normal philosophy is just virtually zero, at the most 5% margin.
Yes.
Of course, when you're aiming for almost zero margin, that may be only in a very localized area of the aircraft. You can't design the aircraft with zero margin everywhere. That much of optimization, probably you may not be able to produce the structure. So there would be areas where the margin may be 2 or 3. There will be area because you will be designing for the critical zone, and rest of the zones, sometimes you can't keep on changing your thicknesses, the weight and all that lies. So you would carry some extra weight, although you will try to optimize as much as you can. So now what happens when you are testing? So you have done all this testing for the coupons, elements, which I'll be talking actually all those details now, but you are just preempting me and let me just talk about it. So the design is done with the allowables, ensuring that you have taken into account the static load, fatigue load, everything together. And there's no chance of the failure of the component because you have already considered all the eventualities of the design. You have done this part of the component testing, subcomponent, just to see that you might have not missed certain unknown factors in design, because sometimes you may get a surprise. We had, during my experience at Boeing, we got a surprise after we have designed the component, and then you find, oh, we should have considered this one, we missed out. So for that, you need to test the component.
Yes.
But component will be tested only up to ultimate load. The design requirement, regulatory requirement is to show the ultimate load carrying capability for 3 seconds. That's it. Then you will, yeah.
Okay,
for certification purpose, you don't want to test it beyond your ultimate. I mean, you just want to satisfy yourself as an organization. You can go ahead and test it beyond ultimate. But regulatory agency is not interested in that.
Okay, Professor. I just wanted to know that whether we should take.
No, if you read the 305.
Yes.
In fact, I quoted in this one. Let me just go and show you that requirement is coming, but let me just show you here. Yeah. Historic strength compliance with the strength reformation requirement must be shown with. Let me see if I. Maybe that I have not quoted here. It is either 305 or 307 saying the testing proof of structure. I'll come back to that exact, but it says ultimate load carrying capability for 3 seconds only. That is what the requirement is.
Okay then.
But I'll give you the exact definition of that. I thought I had included somewhere in this, but really it doesn't seem to. I might have deleted it. Okay, interesting. Any other question? Okay.
Yeah, I have one, Professor.
Yeah, please.
Thank you, Professor.
Yeah. The testing is only done for the nominal design approach. Is it like if we have some deviations with resin pockets or wrinkles or some other deviations. So apart from the nominal design, so do we consider some robust design coupon tests and the variations in the layup and then test them? Then are there any allowables for that?
Okay, let me show you one slide here, but just preempting that. Okay, what is it? Allows and design values, and then I think I have listed just example subcode. Oh, I was looking for this one. Strength and deformation. The structure must be able to support ultimate loads without a failure for 3 seconds. That is a compliance approach. Okay, so this is about 305. Now, as far as your other thing, let me see, where did I include? I thought I have here. Production anomalies. Test metrics. Or did I delete it? I'll look into it. I thought really I had that deviation. Various production anomalies. Material batches, diffusion. Maybe something is missing here. Might have deleted the slides. Test examples. I had it seems some slides are missing here. But anyway, I'll put them. You're having I have got several slides where I've shown that all these deviations which are talking like wrinkles and other production anomalies, we test the coupons and determine the knockdown factors for those issues. So I thought I had here, but maybe.
I think it's okay,
Oh,
Professor.
yes. Oh, sorry. Production anomalies. Yeah. I was looking into some other way. So like, wrinkles, surface depression, and this is what we wanted to know. So
Yes,
you have to determine the knockdown factors for each of these. Now, what happens with these ones? They are not a normal production process. When you are producing a component, you expect it to be defect-free, but there would be always, because nothing is defect-free. Some defects may be there, and which you will be developing during your reliability program as an acceptance criteria that, yes, I'll be accepting that much of defect without changes or without repairing anything. And that is why it is essential to study all those defects which can happen in the production and determine if there is any loss of strength, stiffness, fatigue behavior due to those defects, and what is my allowable, how much damage I can allow, and then what kind of repair. And we had done a lot of work on this, and I was heavily involved in this one. In order to validate, a lot of queries used to come to me. How do I verify this one? Can you suggest the allowable or what is the limit? So, and some of those various other issues I have not included in this one. Was this your question?
Yeah, that was my
Okay.
question.
But I'll talk about that. So in fact, that's what I was wondering. I have included most of the factors which go into the design and certification over here in brief. But I just forgot the sequence. Even though I've seen such a document hundreds of times, but I forget where is what. Okay, now let me go back where we left. Yeah, we're here. Okay. Design certification approaches. In fact, I've talked in brief earlier also, but just to clarify, I'll repeat this one because this is very important again. What are various philosophies by which you could certify the design? There are three types of certification processes. One is certification by test, which is known as a point design approach. Other is a certification by analysis. And third one is certification by analysis, verified by test. So first approach, where what you do, when the company doesn't have significant amount of money and there's only one type of product, they are never thinking of changing the product and doing any different versions of the product. Probably they might live with testing as a point design approach and design certify by testing. What it means, you have a limited amount of data. What you have done, suppose you are designing a flap and you know you're not going to change the material, you're not going to change any of detail later on. So, okay, and you don't have the material allowables, you don't have money for that, developing a significant amount of material allowables. So you'll pick up from some literature, some standard material allowable approximately, and make some gases, put some knockdown factors, design the component, test it. And then you're verifying, okay, my design is okay. And if by strength design, fails at a much higher load, okay, I've just met the margin requirement. If you want to optimize it, well, you could do that. Some kind of, but this becomes too much juggling unnecessarily, because you don't have any sound basis. And moreover, what happens if you want to change anything? You don't have any idea of various design allowables. What do you do? So you have just done one component testing, and based on that, and suppose you want to change something, again you have to test. So it becomes very expensive process. Initial cost, although it may be low, but long-term costs are high. And this approach is not used by the industry. Second approach, certification by analysis. You are certifying a component, you are designing it. Okay, I've got the allowables, methods, applications, everything is certified, so I can do that. Acceptable only if enough confidence in the analysis exists. If your methods are all validated, you can definitely do it by analysis only. And when you have confidence in your design and your product, that nothing will happen without testing. I don't need to test it. Well, it may be possible, but I don't think aircraft industry would ever be happy to design a product based on only analysis. And as such, regulatory requirements do dictate some kind of a testing, which I'll talk about. So that means This also is not possible. Third one, certification by structural analysis verified by test. What this means that you are doing all the design by analysis only in this. However, that analysis has been validated by test. So even though you are doing the design by analysis, but that analysis has been verified by test, which is then approved by FA, and that is what is an acceptable means of certification of aircraft structures. So whether it's Airbus or Boeing or any other aircraft company, they would use this approach only. Any question on these approaches? Romaniel?
Yeah, Professor.
Yeah.
Do we need to, for every analysis, we need to do the test or some limited tests?
Good question. What happens when you have, from your history, you have validated some of the analysis tools? You don't have to repeat that. You have to do the testing only if there's no validation available. Like say, many of the aluminum structure design methods, they have been validated. So you don't have to keep on repeating the test for those methods. But if there are certain different methods which you have not validated, and you want to develop the confidence in that method, even for aluminum, you might test. And composites is a bit more significant because materials are different. So you need to develop the arrivals and then test the element subcomponent component that what you have designed meets the requirement or your analysis method. Because when you are designing a component, like suppose you have designed the flap, of particular using the particular material, like composite materials, using the FEM, Nestran or Patran or Abacus, whichever method. But how do you know that the Nestran or Patran, Abacus, which you are using, is churning out the right information? And especially for stability of the structures, buckling considerations, you need to really test in order to understand the proper behavior of the structure, whether the behavior is being predicted by your analysis type. And that is why the structural analysis methods need to be verified quite often by testing. Once again, as I said, if you have already done particular type of a structure, validated the analysis by testing, then you don't have to repeat it. So you have to have enough confidence that the method which you are using is validated. Is that satisfactory answer?
That's fine, but how do we convince to the regulatory authority? That is what the question actually. We may be having the validation on analysis method, but again,
Yes.
how do we show that compliance?
Okay, there's a process. It's a good question. What happens when you are designing a product and you are trying to show the compliance process? There's a compliance process for that matter. So your regulatory representative would be witnessing your test. The regulatory representative will go through the reports, analysis methods. He or she will go through the testing. They will witness this, and you have to submit the report. I'll be talking about it in my details of testing, in fact, again, let me just show one slide over here. I'm covering this compliance method because that is the main thing. So, excuse me, what this slide is showing is the example from inboard flap testing by Boeing. It's actual, this graph, what you are seeing, it is coming from the test report, Boeing test report, which was published in my paper. So this is actual data. So when we were testing the flap, we had the strain gauges. And by the way, before you test, you have to submit the plan to FAA, the regulatory agency. They have to approve, and you have to show in your, suppose this is a flap, the strain gauges, locations, the design, everything, that is method, and then the compliance method to the regulator, and then test it. I'll talk about the testing. See, this is one gauge result, one principal strains for gauges. And what it is showing as the load is going up, theoretically and test. So what you're seeing here, maximum test, maximum FE. Now, it seems to be too good to be true. You are dealing with such a large structure, and your FEM has predicted particular strain. You are trying to show by the test of the component using the strain gauge that the strain which you are getting from the test is very close to your prediction. And by the way, the requirement was within plus minus 5%. And that is how you're validating that your method which you are using, the finite element method, is able to predict the behavior. Now we're talking about that when I'm discussing this issue, because this is very important, in fact, aspect. How do you validate? How do you verify? How do you show the compliance to the certification agency? And I've tried to cover as much as possible, which is required from my experience on the 787 program. But I'll talk about these compliance methods, and same thing about the leading and trailing edge deflections. And did I have, we had to show the buckling prediction, which was extremely difficult, and talk in detail about the buckling predictions. Okay, so this is what happens, that regulator is continuously involved in whole of the process to meet the compliance. Otherwise, they are not going to certify. They have to sign on all the documents to see the verifications, validation of the design, all the allowables. They had to witness, their representative witness all the allowables testing, coupons, elements, components. Nothing goes without the regulatory eye. They witness, they know everything what is going on. You cannot just work in isolation and then submit finally the data to regulator. No, it doesn't happen. They are continuously involved throughout the process. And I'll talk in detail about this. It's an important aspect. Did it answer your question? Hello?
Yes, Professor.
Yeah.
But you had shown the strain correlation between test and analysis results for different percentage of ultimate loads, right?
Well, yes, percentage, various percentage. You are showing the compliance at every load condition, and if there is a buckling, then they would be deviating, in fact. And then again, and that was the most difficult during our certification testing. That buckling is most difficult to predict, but regulator doesn't care about it because you are trying to design the structure based on your analysis, like nonlinear analysis using a Nestra and abacus. And if you can't show the compliance, your testing strains are not matching with the prediction, they are not then accepting the design. And we had spent a lot of time in correlating the data. It was not as simple as it looks. First time, let me assure you, you make a model, nonlinear model, run it and test it, you may find surprises. There may be buckling, nonlinear buckling, maybe different results. And then you are looking into type of elements, looking into various constraints, whether I have done right or wrong. And that is what then will adjust your buckling behavior. So it looks simple, it's not that. Because nonlinear analysis, which is far more complex. And you got to predict it. That's the problem with the structures. When you're designing for buckling, the prediction of buckling and then matching it is not easy. However, it has to be done. You have to understand the structure. You have to understand your modeling methods, try to correct your elements type, and then we got it. We got it very close to the prediction for the nonlinear behavior. Okay, any more question on that? Hello?
All right.
Okay, but I'll discuss more in detail later on.
Yes, yes.
Okay. Okay, certification analysis verified by test. As I said, analysis, essentially the design is done through analysis. However, that analysis is verified by test, as I've said. So I've just said certification analysis is verified by test. So analysis, certification of structures. That's what it is. However, this is very important. Testing coupon element, subcomponent, component, which provides the reliables and analysis method verification, which feeds into this one. And that is how certification is done, which is a building block approach. We'll talk about building block approach. Usage of composites in aircraft. In fact, some of these slides I've already shown. I want to spend the key driver composite usage, weight reduction, fuel efficiency, cost savings. And I've shown this slide. I would just skip it unless someone wants to discuss again this one. Commercial aircraft failures. Now, I've talked about this history of important commercial aircraft failures and resulting regulations earlier, but just to refresh the memory because it is easy to forget, and I thought just to remind you with various design criteria, because it's important when we are discussing certification, I thought of repeating this information, and I'll just go quickly that earlier, in 1950s, the design used to be essentially based on the ultimate load and fatigue safe life design approach. However, with this approach, the Comet aircraft, first jet commercial transport aircraft, the 3 Comets failed around early 1950s, and that they virtually finished the Comet industry. The major reason for the failures of Comet aircraft, earlier what I've said, was the failure of the windows. They created a cracking, initiated a cracking near the window corners. They were, in fact, the design of the window was really not good because they had a sharp corners and nobody would like to design the window like this one. They are normally elliptical structures so that they don't have the constellation. Now, another the reason was how this design was certified. Quickly, I'll just discuss. So basically, this is supposed to be a good design for the windows. That's what you find all the modern windows to be elliptical. And this was the Comet, which caused a failure, a poor design. However, what happened? I've just added this slide, which was not there in earlier aircraft failure investigations when I discussed. What happened with this Comet aircraft, how it was certified? They tested in fatigue the fuselage. But what happened when the testing was done? The design pressure was 8.25, for which the internal pressure, the fuselage were designed. And they tested at 16.5 psi per cycle load. That is, they doubled the pressure for the fatigue loading, thinking that if they double the pressure, then they would have to test only a few cycles, and then it will be okay for the certification. And comets were certified based on that criteria. But what happened when they tested later on? This slide I'll show before I go back to the previous one. So what they did after the failure investigations were done, when they were doing the failure investigation, they tested the fuselage again, and they tested for the design pressure, fatigue cycle. And to their surprise, they found the fatigue cycles 3057 cycles only. 3000 cycles, the fuselage failed. But when the overloaded fuselage was tested, that is after double the pressure, 16.5 for 30 cycles, and then this pressure, fuselage, when it was tested at the design pressure, it lasted 18,000 cycles. Now, why it is? Anybody has any answer? So when the fuselage tested for double the pressure for 30 cycles and then tested at the normal design pressure, it lasted 18,000 cycles. But if it was not overloaded in the beginning, tested at design cycles only, design pressure only, it lasted only 3,000 cycles. Any thought before I
It is
explain?
because of the overload
Professor,
and
because,
the crack retardation, sir.
Yes, that is what happened.
because of
And
hypothetical stresses, I think.
Pardon?
Because of overloading, some again small load is being applied. Initially
Why?
2 times, then
Yes.
afterwards subsequently less. So some
Yes, this retardation.
then hardening kind of thing.
Yes, that's right. And that is what happened. At that time, really, it was not thought of. Now, this is a practical thing which happened in real structure, the overloading effect. And such a tremendous effect of overloading, retardation effect in the aluminum. So when you are doing the fatigue design of aluminum structures, compared to composites don't show that retardation effect or these load cycles effect normally. But metals are very crucial one cannot ignore when you're doing the fatigue design, the overloading or retardation or sequencing effect. So that is why the testing of the metallic component becomes more difficult in the fatigue than the composite, in fact, which I'll be talking later on. However, I thought that introducing just slide just to show what was the mistake, the blunder committed by. So there were two problems with the Comet failure. One is the design. The windows were rectangular, which had sharp corners. And second thing, the way the compliance was shown, certification. Of course, this is all history, but what happens, it is just to know about the history to get the success. We always learn. So what happened later on? In 1956, an amendment was issued, which dictated the fail-safe design of the structure. And from safe life, fail-safe design. However, even the fail-safe was not satisfactory. If you see in this diagram, then year 1977, Boeing 707 failed in spite of having a fail-safe design. And I'll just discuss it detail in this one later on. But before I do that, then what happened after that? An amendment 45 in December 1978 came into picture, was issued by FAA, which said damage tolerance. And today, every structure has to be designed by a damage tolerance philosophy, which I've talked earlier during my damage tolerance. However, certain structures like landing gear, where the inspections might be practical, then you are designing with a safe life philosophy. Otherwise, it's mandatory requirement that the structures have to be designed using a damage tolerance philosophy. Whether metal or composite, doesn't matter. Then after that, there was a failure of gel, which is a classical failure. I talked about it. This is the worst air disaster in the history of aviation. 521 passengers, 521 passengers died. And then another accident occurred, Aloha B737, Boeing 737 in 1988. And due to some cracking issues, fatigue cracking, and then due to that, Amendment 96 in April 98 came, which stated the wide fatigue damage. And then which dictated a full-scale fatigue testing requirement. So every structure aircraft which is certified has to be tested in full-scale fatigue. And I'll talk about it. Okay, later on, LOV, that is limit of validity, came, damage tolerance of the repairs came into 2000. So various criteria developed. Okay, just quickly.
Professor,
Yeah. Carry on.
what is the reason for issuing this FR26 that 2006? What's the reason actually? Any issue was there?
Oh, this is repairs, damage tolerance. What happened? When JAL aircraft failed, I'll talk about it. Japan Airlines. And there was a problem with the maintenance. Let me just show you. What you see here, this is the history of JAL crash. But let me just sequentially cover various. Dan Air crash made in 1497, which is Boeing model 707, fracture of right side horizontal stabilizer. Fail-safe characteristics of the structure did not perform as intended. It was designed as a fail-safe, but again, fail-safe characteristic, it seems, is not adequate enough to ensure the safety of the structures. And that is why amendment, I said, damage tolerance design. Now, what happened with this one is a horizontal stabilizer core, a spar. So there's a top chord, web, middle chord, lower web, and lower chord. And it seems failure initiated from here, some cracking, and then it propagated also failure. I had included earlier in my presentation the cracking details, but have removed it because it becomes too much. You can read some failure investigation report if you want to know more details about the dyno aircraft failure. Or next time I can show my slide how the cracking propagated, what happened later on. I've got some slides with me. And then Aloha Airline, where the aircraft failed due to the maintenance, to the defect, what happened? Sorry. During maintenance, they did not detect some fatigue cracks which were propagating. And the cracks kept on accumulating, kept on propagating further and further, and caused a fatigue failure. And that is why later on the wide fatigue damage came into picture, WFD, widespread fatigue damage rule design, which I'll talk later on. And that is how issuance of Amendment 96 for widespread fatigue damage. Okay, and that dictated, and that is why it dictates that every aircraft design has to be fatigue tested before certification. So this is the rule 571B to ensure the safety and the widespread fatigue damage. And it has to specify the limit of validity of the life. So Aloha airplane, the primary damage to airplane, total separation and loss of the major portion of the upper crown skin and other fuselage structure. Failure of maintenance during the maintenance, they did not detect the fatigue cracks. Now, what happened here? You see, for this aircraft, outer upper skin, and this is the lower skin, and this is a bond and rivets. Earlier, when this aircraft was designed, they used to have a cold bonded lab chart. The cold bonding might have failed. So during the bond failure, the bond was not taking the load properly, and all the load were taken by these rivets. And rivets you are seeing, they are like a knife edging. So this knife edging created the cracks when bond failed, because as long as the bond is intact, bond will not allow the rivets to carry the load and the structure will be perfect unless the bond fails. But here it seems at that time bond might have failed, which might have not been detected. It's very difficult to detect the bond, actually, the failure. And during maintenance, the cracks which are generated, a sequence of cracks were also not detected. And then gradually, the fatigue crack are initiated, propagated, and caused a sudden failure. Anyway, so that was the history of that. Then Japan Airlines. Now, this is important. Somebody asked a question, how the damage tolerance amendment came into picture. So the history is related to this Japan Airlines flight. So rupture of airplane left pressure bulkhead, explosive decompression was attributed to an improperly executed repair. The repair which was performed was not properly done. And so it led to 521 persons died. The worst air disaster in the history of aviation, and which led to issuance of this document AC 127.3 for repairs damage tolerance. That every repair which we prescribe in our design has to consider the damage tolerance approach for repairs also, not only pristine structures. And I will be talking a few more details during my further lectures when I'm talking about the testing. Now, what was the issue with this one? It's very interesting to understand what happened during maintenance. What this slide showing, the left one is the correct type of repair. It's actual one, so repair should be the actual, the same. What is showing, the upper dome skin, the lower dome skin. In between, there's a splice plate and this rivet. So consider suppose the load is flowing from this skin and it has to go to the lower one. Then the load comes here. This is the rivet. So that means the load on this goes to this one and then shares between this strip and this strip, partly. Okay, due to this. And then when the load is transferred, when this plate is intact to this structure, then because this plate is intact, part of the load goes through this rivet and part of the load is going through this one, because part of the load is going through this, part of the load is going through this one. So this rivet and this rivet would be sharing not equal load, but of course this rivet always will be higher than this one, but not significantly higher. On the other hand, what was done during maintenance? The maintenance personnel, they cut their strip. They splice line plate. Now, can you think of the consequence of cutting this plate? What will happen? This becomes useless. Then all the load which is there, it is not tracking any load. All the load is directly, suddenly, is transferred to this rivet. Because this is not carrying any load now. And what happens, this one, when this transferred on this load, so most of the load is carried by this rivet, which causes the cracking. So gradually the cracks propagated and final failure occurred due to that. So that means during maintenance, proper maintenance not performed, it was not inspected properly, and the damage tolerance, and that is why later on damage tolerance requirements came into picture, that for every repair, the damage tolerance considerations have to be given.
The top rivet.
Yeah.
The top rivet failure, accident happens.
Well,
am I right,
what,
Professor?
Well, what happened? I think
at the top rivet.
No, this one. This will start failing here because this is carrying high load. The cracking starts from here. Now, I'll show another slide, which I have deleted from here, where I had shown basically the cracking picture of this aircraft. What happened? I had a lot of details in my earlier presentations, which I've deleted because it becomes too much. But it's interesting to go through the failure investigation from down. You can download from, internet somewhere, Google. If you go to the JAL, this aircraft accident, you will find various reports about this flight. Or I'll send the report. It's interesting to read if you want to read this. Interesting. But next time I might show the cracking picture. Okay, I think it's already the time. I have already exceeded, and you people might be impatient now to leave. However, I thought probably to cover more slides. Seems way slow anyway. It's good. More questions are there. I'm able to answer and satisfy your requirements. So I think I would stop over here and continue next week. Oh, sorry, on Friday. But if there are more questions, you can ask.
Hello, sir.
Yes, please.
I'm Arvind Yadav. Nice to see you again, sir. Yeah.
Hi.
Yeah. So I have a question like a metal for the composite can be used the SN approach for predicting the fatigue. Like damage tolerance, of course, is as per the certification, it should be used damage tolerance for the composite structure, explicitly mentioned in the FR 23. But if someone want to do the based on the SN life approach, will be okay or not? If he has the
as far as certification is concerned, certification wants a damage tolerance approach. You need to ensure that the large damage, small damage, you are complying with that in order to meet the certification requirement. For 25, I do not know 23. 23, what are the requirements for damage tolerance for 23? I will look into. I have never really looked into the details. But
23 for the small utility aircraft, they also tells it should be the damage tolerance.
Okay, so you got to meet the damage tolerance requirement.
Yeah, but if we like for the study point of view, if we have the sufficient data on the SN curve for the composite given composite laminate, then doing the SN life approach will be the appropriate or during the design phase.
Okay, you're talking of fatigue only. How about the static one? Static damage tolerance.
I'm telling for the fatigue only, sir.
For fatigue, we show that no growth approach.
Yes, sir.
You know, that is a
kind of safe life approach.
Yes, no growth approach. Yeah, similar to, you can consider that. But here, come on, what is happening? I was trying to show this. If you might remember this, my damage tolerance diagram. I'm not sure whether 23 also has similar type of requirement or not. I would admit that I don't remember, but for 25, this requirement has to be met, and this is what, so damage tolerance requirement have to be met using all these various phases. And I'll talk about it next lecture, although I have talked earlier about damage tolerance in detail, but again, just for the continuity of this presentation. Right.
So 23 also explain like that only.
Okay.
The residual strength should not go below the limit loads anytime. Before that, it should be repaired and bring back to the original ultimate limit.
So it's the same requirement.
Yeah.
For that. Okay.
So means from the like we used the safe life approach for the metallic. If we have the sufficient data on the SN curve for the composite laminates, doing the study based on the SN life approach, will be appropriate or not? That was my question.
Yeah, that's okay. That's what we do. In fact, safe life, that's what endurance limit approach.
Yeah, correct. Because in the design phase, if we go with the
you can't do the propagation type like you do the metal. No, that's not possible. I misunderstood your question.
Okay.
And I'll talk about that. In fact, one of the slides here I have shown fatigue design endurance limit approach. That's what we would discuss.
Yeah. For the for composites.
Yes, composites, not for metals.
Please put more time on that, sir.
So it's like a safe life. You are right.
Yeah, that point of view.
Okay. Any other
Thank you,
question?
sir.
Any other question before we close? Otherwise, good evening, and we see you on Friday.
Thank you a lot, sir.
Okay. So
you.
Dinesh, thank you.
Thank
Everybody.
you very much, Dr.
Yeah.
Garg.
Thank you very much,
Dinesh, sir.
Bye.
professors.
Thanks to the audience also.